Hello everyone, welcome to the course Basics of Materials Engineering. In week 13, we'll be having a summary session. So, this course is offered by Professor Ratna Kumar from Department of Mechanical Engineering, IIT Madras, and I am your TA, Alka Jangit from IIT Kanpur. In first lecture, we studied about crystalline solids. So, firstly, in case of solid materials, they show a regularity of the atomic and ionic arrangement. So, if there is a long range structure that exists in which atoms are arranged into unit cells, and the unit cells they repeat in a regular or orderly pattern, it forms a 3D lattice. So, this is your crystalline type of solids. In this, each atom is bonded to its nearest neighbor, and some of the properties they depend on the crystal structure. For example, these have directional properties because of the ordering, and they show an isotropic nature. So in different directions you'll be finding your mechanical properties or optical properties to be different. These have sharp melting point, and all metals and many ceramics and some polymers they form crystalline structures under normal conditions. Examples are gold, silver, aluminium, etc. This is what your crystalline structure looks like. And then there are polycrystalline solids. In nature, when we discover the solids or we manufacture them, they are commonly polycrystalline rather than single crystalline. So these are made up of an aggregate of many small single crystals, which are also called crystallites or grains. And across the grain boundary, the orientation of the crystal changes. So, and the grains are usually 100 nanometer to 100 micron in diameter, and the polycrystalline materials have a high degree of order over many atomic or molecular dimensions. The polycrystals with grains that are less than 100 nanometer in diameter are called nanocrystalline materials. And most engineering materials are polycrystalline, and properties may or may not vary with direction. So, in case of, for examples, common steels are polycrystalline, and if grains are textured due to rolling or extrusion, then they show an isotropic type of behavior. And if grains are random, then they will be showing isotropic behavior. So the elastic modulus will be same in all directions. So this is what your polycrystalline material looks like. These are various grains having different orientations. Next is single crystal. In this, only one grain will be there and there won't be any grain boundaries. And these are formed by uniform cooling or of liquid material. These have high degree of order throughout the entire volume of material, and these are useful for applications where grain boundaries are harmful. For example, at high temperature deformation or creep resistance, as creep takes place by grain boundary sliding. So single crystal turbine plates which use nickel based superalloy, gas turbine plates, these withstand creep at very high temperatures due to lack of grain boundaries. In case of diamonds and semiconductors as well, these are single crystals. Amorphous solids, in these the atoms or molecules are arranged in an irregular manner. These don't have any periodic packing, and there are no directional properties, and they show isotropic type of properties. These occurs for complex structures and when there is rapid cooling in case of metallic structures. And some examples are glass, plastic, rubber, etc. This is your polycrystalline, this is your single crystal, and this is your amorphous type of structure for silica. crystal systems. In this case, your lattice and your basis, they combined give you crystal structure. Lattice will be a mathematical representation and basis will be an atom or a molecule. So in case of lattice, it has array of points in space in which every point has an identical environment with respect to all other points. And in case of basis, it is a single atom or group of atoms which are identical in composition and orientation in space. Now this is the lattice, which is just points, and when you put some molecule or some atom at these points, then you'll be finding crystal structure. These are various crystal systems which are cubic, hexagonal, tetragonal, rhombohedral, orthorhombic, monoclinic and triclinic. And these are axial relationships and interaxial angles. Based on these are various crystal systems. First is simple cubic. In this case, the unit cell consists of 8 corner atoms, and all these corner atoms, they contribute only one effective atom for the lattice, because the atom, it's shared by 8 other unit cells surrounding this atom, and so 1/8 part will be inside this unit. So 1/8 times 8 will be your 1 atom per unit cell. And for packing fraction, you take the volume of your atoms inside unit cell divided by entire volume of unit cell. So as for 1 atom, it is considered spherical, so 4/3 pi r cube. R is the radius of atom. A cube, A is your lattice parameter A. So in case of simple cubic, your A will be equals to 2R. So it will give you packing fraction as 52.4%. And coordination number will be the number of atoms that are immediately surrounding a central atom in a crystal. And for simple cubic, it is 6. And simple cubic is rare due to poor packing, and it is found only in polonium. Second structure is body centered cubic. In this case, along with corner atoms, there will be one more atom at the body center. So the effective number of atoms will be 2. And packing fraction, in this case, your A will be equal to 4 upon root 3 times R. So your packing fraction will be, and here you have to multiply with 2 because you have 2 atoms inside unit cell. So packing fraction will be 68%. And in case of BCC structures, they have 8 corner atoms and 1 body center atom. And coordination number will be 8, and examples are chromium, iron, molybdenum, potassium, sodium, tantalum, vanadium, etc. Next structure is face-centered cubic. Here, along with the corner atoms, you have atoms at the center of faces. So this face center atom is shared by 2 units. So this face will be common in 2 units. So this will be shared by 2 units. So it will be half inside this unit. So half times 1/2 multiplied by 6 atoms at the faces, because it has 6 faces, plus corner atoms. So the total contribution will be 4 atoms per unit cell. And for finding out your packing fraction, you can, in this case, A will be equal to 4 upon root 2 times R. So packing fraction will be 74%. It is the highest for this one and HCP, So FCC structure has 8 corner atoms and each face has one center atom, and coordination number will be 12. And example will be aluminium, copper, gold, silver, lead, nickel and platinum. And in case of Miller indices, so these are the designations of the planes and directions in the unit cell, and the number of indices will be matching with the dimensions of the lattice or the crystal. Example will be in 3D. The unit cell has 3 indices HKL. Here you won't be using any commas, and these are the various symbols that I used. In case of your small brackets, you use for individual plane, and in case of this curly bracket, you'll be using for family of planes, and square bracket will be used for individual direction, and triangular bracket is used for family of directions. For Miller indices for a plane, this is, in this case you find out where your plane will be intersecting these axes. So if in case of this it is intersecting at 1 for all axes, and then you have to take reciprocal of these intercepts, and after one's reciprocal will be 1, so then you have to modify the reciprocals. If those are in fraction, then you have to eliminate fraction, you have to multiply it with a number, so these all become an integer. Then you have to also reduce multiples, and then you have to put the your integers in brackets, and if it is negative then you have to put bar on it. So in this case your plane is 1 1 1. In case of direction, you can create a new origin as well. So in this case you can shift origin, and according to that you can give new designations to new directions, x dash, y dash, z dash. Here you have to find out how you are reaching at the end point from the start point. So from O dash you are walking, in case of x direction you are walking one distance of 1. So 1 will be x direction. In y direction you are walking in negative side, so it will be -1, and z also you are walking +1. So 1 1 bar 1 will be your direction Miller indices. And your second chapter is crystal your defects. So in this case, firstly, classification of crystal defects. In case of any deviation from crystal's completely ordered arrangement, it will be called a defect or imperfection. And properties of materials are influenced by the presence of imperfections, and mechanical properties of pure metal, they change significantly when metals are alloyed. So firstly, classification is based on their dimensions. In case of 0 dimension, there are vacancies, interstitials, substitutional defect, Frankel defect and Schottky defect. In case of 1D, you have edge dislocations, screw dislocation and mixed dislocations. These are also linear defects. 2D are interfacial defects. In this case, you have grain boundaries, twin boundaries and free surface. In case of 3D or volume defects, you have voids, cracks, these defects. Now there are also some advantages of defects. Because of defects, you can get alloying of metals, which can give you better mechanical and other properties. Metal deformation. So deformation is also only possible by the existence of your dislocations and vacancies. Composite formation, that also requires some addition of defects. Strengthening, mechanisms which mainly depend on addition of either grain boundaries or another impurities or some dislocations. Electronic devices using semiconductors, in this case you dop your materials using other elements, and carburizing, nitriding, these heat treatment and surface hardening, these also require movement of atoms, thus inclusion of some defects. One of the important defect is vacancy defect, which is always present in materials. So when an atom is missing from its regular lattice site, it is called a vacancy, and it is impossible to create a material free from vacancy defects, and presence of vacancies increases the entropy and disorder in the crystal. It also decreases the density of the substance, and the concentration of vacancy increases as you increase temperature, because there is more energy available for this atom to jump around in the lattice, and decreasing activation energy. This is possible by changing your material system. So for example, if you are taking lead and iron, in that case lead has lower melting temperature, so it is more likely to form higher number of vacancies at the same temperature. The energy required for the formation of vacancies is the QV. So in this case, equilibrium vacancy concentration is equals to exponential minus QV divided by kBT. kB is your Boltzmann constant, T is your temperature. Now various questions are asked on Schottky and Frankel defect as well. So in this case, these are defects that are found in ionic solids. So for example, here in NaCl, it is shown that if there is one cation and one anion are missing, so it is the pair of vacancies. So pair of cation and anion vacancy will be your Schottky defect. In case of Frankel, you will be seeing some cation will be missing from its original site and it will be found in interstitial site. So in both cases, your solid will remain neutral, and it is due, in case of Schottky defect, it is due to equal number of cations and anions are missing from the lattice, and it results in decrease in density of crystal. And this type of defect is found in highly ionic compounds with high coordination number, for example NaCl, CSCl and AgBr. In case of Frankel defect, it is due to missing of ions, usually cations, from the lattice sites which occupy in interstitial sites, and it has no effect on density of crystal. This type of defect is found in crystals where the difference in size of cations and anions is very large. For example, AgCl, AgBr and zinc sulfide, etc. Effect of point defects. Now in case of intrinsic point defects, they exist in equilibrium concentrations, for example vacancies, and the defect concentration may be increased by processing. These are three techniques that are used for increasing number of vacancies. It can be either quenched, your material, if you are quenching it from high temperature to lower temperature at very fast rate, the number of vacancies will be very higher. And in case of plastic deformation as well, you can introduce vacancies and dislocations. And irradiation, in this case, it does not have side effects such as production of dislocations, and there will be vacancies produced. In this irradiation also leads to radiation damage. And in case of solids, in pure metals consisting of only one type of atom just isn't possible. So there are very sophisticated techniques. They lead to purity of only up to 99.9999%. You can go beyond that. At this level, there are around 10 to the power 22 to 10 to the power 23 impurity atoms in a cubic meter of material. And most familiar metals are not highly pure, they are alloys. An addition of impurity atom to the metal, they can lead to formation of solid solutions. So in case of solid solution, you have two parts. First is solvent, which will be element or compound that is present in greatest amount, also called host atoms. And solute will be element or compound present in minor composition. So these green atoms, they are your solvent atoms. And a solid solution is formed when solute atoms are added to the host material and the crystal structure is maintained. And impurity point defects are observed in solid solutions. Now there are two types of solid solutions that are possible. If it is residing in voids, small atoms, then they will be interstitial type of solid solution. And if the size of atom is equivalent to the size of your solvent atoms, then it will be forming substitutional solid solution. Now in case of substitutional solid solution, they can be formation of isomorphous system. So in this case, copper and nickel are completely soluble in each other at all proportions, and here substitutional solid solution forms. The atomic radius of copper and nickel are very close and both have FCC type of structure, and also electronegativity is also very close. And there are valences are +1 and +2. And other examples of isomorphous systems are copper gold, gold silver, nickel palladium, lead tin, and tin bismuth. Lead tin is eutectic, so I think these are the examples of solid solutions, substitutional solid solutions. Now solid solutions for interstitial. In case of impurity atoms that fill the voids or interstices among the host atoms. In case of metallic materials with very high packing factors, the interstitial space is very less, and atomic diameter of interstitial atom should be much less compared to host atoms. And the maximum allowable concentration for interstitial impurity is 10%, because as you keep on adding the amount of interstitial atoms, the more stress will be there in strain. There will be lattice strain in your lattice, so it won't be forming isomorphous type of system in case of interstitial solid solutions. Carbon forms an interstitial solid solution when added to iron. In case of iron carbon system, this carbon forms interstitial solid solution when added to iron, and their atomic radius has huge difference, and the maximum concentration of carbon in iron possible is 2.1%. Now 1D defect will be dislocations, and the dislocations are linear or one-dimensional defect around which one of the atoms are misaligned. Within the region around the dislocation line, there is some localized lattice distortion, and the atoms above the dislocation line are squeezed together, and below they are pulled apart. So above you have compressive type of strains, and below you have tensile type of distortion. The magnitude of this distortion decreases as you keep on going further from this dislocation line. This is how dislocations looks under TEM. Now two types of dislocations are there. First is edge dislocation, second is screw dislocation. They can be mixed dislocation as well, which will combine both of their character. Now this is what edge dislocation will look like. In this case, as you are applying shear stress in this direction, so the dislocation line will move in the direction of the applied shear stress. So this dislocation will move in this direction. And in this case, screw dislocation, your dislocation line moves in the direction perpendicular to the applied shear stress. But in both the cases, plastic deformation will be same. Berger's factor, it is the magnitude and the direction of the lattice distortion associated with the dislocation, which is expressed in terms of Berger's factor. So if you have perfect lattice, then there won't be any Berger's factor, so your circuit will be completed. And in case of where there is presence of dislocation or other defects, this Berger circuit, it won't get complete. So if you walk same number of steps in each direction, then you will be requiring an vector to join this circuit. Now for metals, the Berger's vector will point in a closed pack direction with a magnitude equal to the interatomic spacing. And dislocation density is the total length of dislocations per unit volume of material. And in case of carefully solidified metals, you have very less dislocation density, which is 10 to the power 3 mm per mm cube of crystal. And in case of heavily deformed metals, you have around 10 to the power 9 to 10 to the power 10 mm per mm cube. Now slip systems. Dislocations prefer to move in preferred planes, which are called slip planes, along the preferred directions called slip directions. Now slip system is a combination of slip plane and slip direction. So for here, in case of FCC type of unit cell, you can see that 111 type of plane is the mostly packed plane, and the direction is 110, which is also close packed. Now along 110 direction, your dislocation will move. And a slip system depends on the crystal structure. So for a particular crystal structure, you will be having a specific crystal slip system. The choice is such that the atomic distortion due to dislocation motion is minimum. So in this case, your planar distance, it will be the lowest, so that it encounters less valley type of structure, so that it can move smoothly. Other interfacial defects. So first is stacking faults. In this case, in case of FCC and HCP, these have different type of stacking sequence. So if one plane is either missing or one extra plane is there, then there'll be formation of stacking faults. Phase boundaries are found in multi-phase materials, and in case of ferromagnetic or electric materials, we see domain walls. So it will be a boundary that will be separating different magnetic orientations. The atoms at the boundary, they are less regularly arranged and bonded, so they have higher energy. In case of high angle grain boundary, we see higher energy, and at low angle grain boundary we see low energy. So grain boundaries are more chemically reactive due to this higher boundary energy. So when you apply some chemical on your material, then these grain boundaries are more likely to undergo corrosion earlier compared to crystalline part. So that's why you can see the grain boundaries under microscope. These impurity atoms, they attach here due to the higher energy state. Strengthening mechanisms in metals. The ability of a metal to plastically deform depends on the ability of dislocations to move. Thus, restricting or the hindering dislocation motion makes a material harder and stronger. Some mechanisms to strengthen metals are as follows: grain refining, solid solution strengthening, strain hardening, precipitation strengthening, martensitic strengthening, and composite strengthening. First is grain refining. In this case, a fine grained material, one that has small grains, is harder and stronger than a coarse grained material due to a greater total grain boundary area to restrict dislocation motion. Dislocation motion is what deforms your material. So if you are restricting dislocation motion, you will be making your material more hard and more having higher strength. So sigma naught will be equals to sigma I plus ky upon delta t. This is the Hall-Page equation. In this case, sigma naught is yield strength of material. Sigma I is a frictional stress which opposes the motion of dislocation. It is uh, it is given for a material. It is specific for material. Ky is extent to which dislocations are piled up. This depends on plastic deformation of material or what type of manufacturing process that is used. D is your average grain size. The critical grain size, which is typically around 10 nanometer, the yield strength would either remain constant or decrease with decreasing grain size. The phenomena is known as inverse Hall-Page relation, and equation is not valid for very large and extremely fine grains. Second is solid solution strengthening. In this case, you will be adding some other element atoms that can be, depending on the size, you can get either substitutional type of solid solution or interstitial solid solution. In case of substitutional, your atom can be smaller than the atoms of host atoms. In this case, you'll be having compressive type of stresses. And if you have atoms, your solute atoms larger, then there'll be tensile type of stresses. So in this case, you'll be having tensile because the bond length is increasing. In this case, it is decreasing, so you will be having compressive type of strains. And in this case, alloying with impurity atoms that go into the substitutional and interstitial locations improves strength and hardness. Because of these strengths, your material strength is improving. In case of high impurity metals, they are softer compared to alloyed materials, and alloys are stronger because of lattice strains on surrounding host atoms. Lattice strain field interaction between dislocations and impurity atoms inhibit dislocation motion. Third method is strain hardening. In this case, you apply some plastic deformation, then your material strength will be improving. In this case, strain hardening is the phenomena whereby a ductile metal becomes harder and stronger as it is plastically deformed. It is also called work hardening or cold working because the temperature at which deformation takes place is lower than the melting temperature. And the effects of strain hardening may be removed by annealing heat treatment, which is slow heating and slow cooling, and strength increases but ductility is sacrificed in this method. Fourth is precipitation or edge hardening. In this technique, It is used to increase the yield strength of malleable materials like aluminium, copper alloy, or stainless steels. And based on changes in solid solubility with temperature to produce fine particles of an impurity phase which blocks the movement of dislocations in crystal's lattice. And alloys must be kept at elevated temperatures for hours to allow precipitation to take place. This time delay is called aging. Now, in this case, this is copper aluminium alloy. In this case, these are the GP zones or theta prime. These phases are forming with increasing temperature. So, in this case, you have to first solution heat treat your material, then it is quenched, then you have to heat it again at a lower temperature for formation of these precipitates. Now, fourth lecture was on mechanical properties. In this case, first term that is very important is stress. This is the internal resistance force per unit area acting on a material, and it uses the original cross section. This is engineering stress, or in that case conventional stress, you use original cross section area of the specimen. So stress will be force divided by original area. Unit will be Pascal or Newton per meter square. Strain is defined as the change in length per unit original length. It is unitless and also known as engineering strain or conventional strain. And E strain will be equals to delta L upon L naught. Sometimes strain is expressed in microstrain, which will be 10 to the power minus 6. In case of deformation, in elastic part, we see that stress is proportional to strain, and the behavior of solid is linear elastic, and the constant of proportion is called elastic modulus. So sigma is equals to capital E times E. It is also holds good for stresses and strain in simple compression. And in case of shear type of stresses, we see that tau is shear stress equal to G shear modulus times shear strain. And in case of pressure, so it is proportional to negative of the dilation volumetric strain, and then you'll be getting bulk modulus, which is K. Other properties that are important is elastic limit. It is the greatest stress that a material can withstand without any measurable permanent strain after unloading. Yield strength is stress at which a material begins to deform plastically, and it is in case of yield strength can be easily defined in case of some ferrous materials, but in case of non-ferrous materials, you have to find out it by taking a parallel line to the this linear part by taking offset by 0.2% strain. And in case of tensile strength or ultimate tensile strength, it is the maximum load P maximum divided by the original cross section area. This is the maximum stress that a material can withstand. Elongation, percent elongation will be your final length. At this point, your final length minus initial length divided by initial length. And percent reduction in area will be initial area because it will be larger minus final area divided by initial area. This final area will be at the lowest area where necking will take place. True stress and strain. In this case, in case of engineering, we divide by original cross section and original length, but in this case, you have to divide by instantaneous cross section and instantaneous length. Now true stress, true strain curve gives a true indication of deformation characteristics because it is based on instantaneous dimension of the specimen. And in engineering stress strain curve, stress drops down after necking since it is based on original area. In true stress strain curve, the stress however increases after necking since the cross sectional area of the specimen decreases rapidly after necking. And the flow curve of many metals in the region of uniform plastic deformation can be expressed by the simple power law. So in this region, above your yield point and between UTS, this equation can be given by sigma t equals to k times Et times n. Here sigma t is your true stress, Et is your true strain, k is your strength coefficient, n is your strain hardening exponent. Ductility and brittleness. Ductility is the measure the degree of plastic deformation that has been sustained at fracture. So it will be your percent elongation. Now strain at fracture is, if it is percent elongation is greater than 5%, then your material will be called ductile, and it has well defined yield point in this case. And in case of brittle material and the property brittleness, it will be a material that experiences very little or no plastic deformation upon fracture. And the strain at failure is less than 5% and it does not exhibit identifiable yield point. Now in this case, this one is your brittle fracture and this is your ductile fracture where a lot of elongation is occurring and necking will also take place. Now other property is resilience. It is the capacity of material to absorb energy when it is deformed elastically and then recover same upon unloading. And the modulus of resilience, which is the strain energy per unit volume required to stress a material from an unloaded state up to the point of yielding. The SI unit is joule per meter cube. This is the formula that is used. So it is this is your up to this point yield strain. So EY times the your sigma y yield stress, and this is as a, it is triangular type of shape, so it is multiplied by half. And the resilient materials, they have high yield strength and low modulus of elasticity, for example beryllium, copper, and these type of materials, they are used for spring application. Other property is toughness. In this case you have to take in consideration entire area below this curve up to fracture point. Now the materials which will be having higher tensile strength as well as high ductility will be showing high toughness. Toughness is measure of ability of material to absorb energy up to fracture. It is represented by the total area under stress strain curve up to fracture point. Brittle material has comparatively high yield and tensile strength but low toughness due to lack of ductility. And ductile materials are tougher than brittle ones. So as shown here, multiple these green graph, it shows for metals. In this case these have high tensile strength as well as high ductility, so they have large toughness. And in case of ceramics, these have high tensile strength but very less ductility, so they have very small toughness. In case of polymers, they have very large ductility but very low tensile strength, so they have very small toughness as well. Impact testing. In these tests, load swings from a given height to strike the specimen, and the energy is dissipated in the fracture is measured. And metallic samples, they tend to be square in cross section, while polymeric test specimens are often rectangular. The factors that affect the impact energy for a given material, the impact energy will be seen to decrease if the yield strength is increased. So materials with high yield strength will show less impact toughness. The notch also serves as stress concentration zone, and some materials are more sensitive towards notches than others. For example, metals are more sensitive compared to polymers. Factors which affect the yield behavior and hence ductility of a material, such as temperature and strain rate, will affect the impact energy. Now, from this graph, we can see that in case of metals, they show higher impact toughness compared to ceramics. Polymers and composites, they show optimum impact toughness. Other property is hardness. It is the measure of a material's resistance to localized plastic deformation, which can be either small indentation or scratch. Advantages of hardness testing. These are simple and inexpensive to perform, and there is no special specimen preparation is needed, and the apparatus is relatively cheaper. And in case of this is non-destructive method, there will be only small indentation, which is only deformation. Other mechanical properties like tensile strength and fatigue strength, they can be obtained from the hardness data. So there are some empirical relationships for steels and copper based materials which can give you these strengths as well. Three types of hardness measurements are there. First is scratch hardness, which is used by mineralogists, and indentation hardness is used by engineers. Rebound and dynamic hardness is also used, and these are the hardness, these are and various hardness number formulas that might be helpful for exam. So in case of Brinell, indenter is 10 mm steel or tungsten carbide ball, and for Vickers use diamond pyramid having an apex angle 136 degree. For Knoop, diamond pyramid is used, and for Rockwell hardness, diamond cone or 1/16 inch diameter steel ball is used. Now based on these, this diamond indenter is called Braille indenter, and based on this the formula used is 100 minus 500 T, while for this steel ball indenter the formula used is 130 minus 500 T. T is your depth of penetration in case of Rockwell hardness. And these are the formulas that are used for Brinell hardness, Vickers hardness and Knoop hardness. Other property is fatigue. The fatigue strength of a material is the maximum stress at which failure may occur after a certain number of cyclic load applications. So a component is designed to give a certain length of service under a specified loading cycles. Such tests are plotted as graph of applied stress against the logarithm of number of cycles of failure, and the curve is known as SN curve. So for example, in this case, these are the number of failure cycles in log scale, and maximum stress is on y direction. And here in case of ferrous materials, we'll be finding that they have a endurance limit because of strain aging, while in case of non-ferrous, not such uh, identifiable uh, endurance limit will be there. So in this case, we specify particular number of cycles, for example 10 to the power 6 in non-ferrous metals, and corresponding to that stress limit is taken as a fatigue limit. Creep, this is the permanent deformation under constant load over a period of time. This is the dependent on temperature. So a creep test involves a tensile specimen under a constant load maintained at a constant temperature, and at relatively high temperatures creep appears to occur at all stress levels, but the creep rate increases with increasing stress at a given temperature. The applications are in studying material behavior at elevated temperatures, such as turbine plates, nuclear reactor components, jet engines, heat exchangers, etc. And this creep, as we see at this graph, we can see that it occurs in three stages. So at the first stage, it is primary stage, where it occurs at beginning of test, and creep is mostly transient. In secondary stage, your rate becomes constant. Here creep rate is roughly steady. In third stage, your creep rate begins to accelerate as the cross section area decreases due to necking, followed by a failure, which is known as rupture. Now fifth chapter is based on failure. So in failure, it occurs when material starts exhibiting inelastic behavior. In case of brittle and ductile materials, they have different modes of failures, and this depends on loading. In case of ductile materials, they first exhibit yielding, then plastic deformation before failure, while brittle materials, they don't show any yielding, and they fail directly. So factor of safety is dependent on this. In case of brittle materials, it is taken based on your failure load, because no yield point is there, and sudden failure takes place. And in case of ductile materials, they have well defined yield point, so factor of safety is applied on yielding. And in case of fracture mechanics, failure occurs when stress and crack geometry. In case of fracture mechanics, we assume that there is always pre-existing cracks exist, and these two combined are greater than material fracture toughness. And when we talk in general as strength of material, then we assume that fracture occurs when stress exceeds the material strength. Now in static tensile test in general, ductile materials are limited by their shear strength, and brittle materials are by their normal strength. Hence one kind of failure theory doesn't explain all the materials, and different failure theories for the two class of materials is taken. But before talking about the failure theory, a proper definition of failure itself is important. And in case of ductile materials, they are defined as they have elongation up to fracture greater than 5%, and for many ductile materials this number is usually 10%. A component may be considered failed if it yields and deforms sufficiently large, leading to improper functioning. A component might fail by fracture, and both the conditions are failures, but mechanics is different. In addition, the loading can be static or dynamic. Firstly, we'll be focusing on static failure. So in case of ductile materials, they fail by fracture if loaded beyond the ultimate tensile strength. and typically the machine components made of ductile materials are considered to be failed when they yield under static loading, and yield strength of a ductile material is much less than the ultimate strength. Now, in case of fracture mechanics, there are three types of loading. First, mode 1 is opening mode, second is mode 2 is sliding mode, mode 3 is tearing mode. And Griffith's experiment, based on this you find this equation. So firstly, like surface tension in liquids, solids also possess surface energy, because at surface your atoms they don't have all the bonds completed, so because of that they have extra energy. So in case of bulk atoms, they are surrounded by similar environment compared to atoms at surface. So for the atoms on the free surface, a few layers below the free surface, there is only bonding force from beneath and nothing or very little from above. As a result, the surface layer of atoms, they experience strain, and the deformation of the surface atoms, they require some energy called surface energy. And so based on this, Griffith hypothesized that the crack in material advances when the released energy, which is incremental energy released, it exceeds the energy required to create two new surfaces. Now, elastic strain energy is given by this formula, pi c square sigma square upon E, and surface energy is given by 4c gamma c. Now, we equate both of these equations and we find the value of sigma, which is your fracture stress, based on the size of crack and elastic modulus, and gamma s is your surface energy. Stress intensity factor, this is when your material already has a pre-existing crack, so your strength of material will reduce and it will be based on your stress intensity factor. KIC is your fracture toughness, Y is your geometric constant, sigma is stress, A is your critical internal crack length, and the relation will be KIC equal to Y sigma times under root pi A. Now, various types of fractures. So this one is your highly ductile type of fracture, with where specimen necks down to almost a point. This is your moderately ductile fracture after some necking, and there is a brittle part as well. In this case, this is completely brittle type of fracture without any plastic deformation. In case of brittle fractures, cracks may spread extremely rapidly with very little accompanying plastic deformation. Such types of cracks may be said to be unstable, and crack propagation once started will continue spontaneously without an increase in the magnitude of the applied stress. Next chapter is fatigue failure. In this case, Waller found that the number of cycles of time varying stress is the culprit for the failure of various materials. He took around 20 years for this research. He found out that the existence of the endurance limit for steels, for example, a stress level that would be tolerable for a millions of fully reversible cycles. Now this is what SN curve looks like. So at the y-axis there will be amplitude of your stress, and at the x-axis there will be log number of cycles. These are various time varying stresses that are applied in case of fatigue. So first one is reversed stress cycle. In this case, your stress alternate from maximum tensile stress to maximum compressive stress of equal magnitude. And second is repeated stress cycle, in which maximum and minimum stresses are asymmetrical relative to the zero stress level, and the mean stress, range of stress, and stress amplitude are indicated. Random stress cycles are won't be having a particular uh, stress amplitude. Now these are various parameters, fatigue loading parameters. So based on your cycles, you can find out cyclic stress range. This will be sigma maximum minus sigma minimum. Stress amplitude will be your sigma this stress range divided by 2. Mean stress will be your average, so sigma maximum plus sigma minimum divided by 2. Stress ratio will be sigma minimum divided by sigma maximum, and amplitude ratio will be sigma amplitude divided by sigma mean. In case of your fully reversed loading, you will be having stress ratio as -1 and amplitude ratio as infinity. And in case of repeated loading, you will be having R is equals to 0, A will be 1. Now SN curves. So fatigue is the fracture failure of a material that is subjected to repeating cyclic loading or cyclic stresses. There are two factors. First is magnitude of loading, which will be S amplitude on y-axis, and the other is number of cycles before the material fails, that is on x-axis. The behavior is different for different materials, so it is customary to show the fatigue behavior of a given material in terms of an SN curve. Here S denotes the stress amplitude and N denotes the number of cycles before the material fractures. In each cycle, the stress is raised to a maximum value in extension and reversed to the same value in compression. So as I told earlier, these in case of ferrous materials, you will be having an endurance limit. After that, up to million cycles you can go below this stress and you won't be seeing failure in material, while in case of non-ferrous materials you don't have this type of endurance limit. Now there are 3 stages of fatigue failure. First is crack initiation. Your crack is starting from here, and then the first stage involves a very short duration. Cracks initiate due to stress razors such as notches, and it is important for ductile material due to local yielding. Second is crack propagation. In this, the second stage involves most of the life of the part. Tensile stress opens the crack and compressive stresses close the crack. Now, crack propagation growth rates are very small, which are 10 to the power -8 to 10 to the power -4 inch per cycle, and final stage is sudden fracture. In this region, we'll be seeing brittle type of failure in this area. So this stage is very instantaneous. In this case, it occurs due to unstable crack growth because the cross section remaining for the part is very less to support the stress. Now the factors that affect fatigue life. First is mean stress. As the mean stress increases, the fatigue strength decreases, and these surface treatments introduce some compressive stresses on the surface of material. These are short peening, case hardening by nitriding, carburizing, etc. And these enhance fatigue strength of steels, Third is design factors. So if there is any notch or geometrical discontinuity that can act as stress region, and fatigue crack can initiate on these sites. Fourth is environmental factors. These are, for example, at high temperatures or existence of some corrosive environment, these can lead to increase in fatigue. These are the, as you can see here, as the mean stress is increasing, so you can see that fatigue is increasing as fatigue strength is decreasing. And in this case, if graph is coming down, because if the material is short pain, then it is showing better fatigue strength. Now the theories for fatigue. First is Oregon theory. In this case, it assumes that there are some weak regions present in the crystal. For example, the metal can contain some small weak regions along which the slip occurs easily. So the metal also contains inclusions, impurities which act as notches and cause stress concentration around inclusion. These regions are treated as plastic regions in the elastic matrix, and they experience an increase in stress even when the repeated applied stress is constant. This increase in stress causes plastic strain in the weak region, and this plastic strain increases when the increase in applied stress on the specimen. When the plastic strain in the weak region exists beyond a certain value, crack will get formed and this will propagate. Now in this case, we can see that this grain in between, it is favorably oriented for the slip compared to the loading direction. So this will act as this is more likely to undergo crack initiation. Second theory is fatigue limit theory. In this case, localized strain aging affects the fatigue properties to a large extent, and some metals have well defined fatigue limits while others do not show fatigue limits, and the metals which undergo strain aging have well defined fatigue limits. A specimen with less amount of nitrogen and carbon will have less tendency for strain aging, and the SN curve will not show fatigue limit for this specimen. Heat treated steels, they show a definite fatigue limit. Third is Wood's theory. In this case, formation of these intrusion extrusions takes place. So the strain direction in fatigue is reversed again and again, and this so the strain direction in fatigue is reversed again and again. So the slip produced by fatigue consists of slip bands, which are the slip movements of the order 10 to the power minus 8 mm in length and 10 to the power minus 6 to 10 to the power minus 5 mm in height. Now these formation of these extrusion intrusions, they lead to formation of initiation of crack. When there is a strain in one single direction, the steps that appear are simple, and when the loading is cyclic, the slip bands tend to group as notches or ridges. These notches, they act as starting point for fatigue crack. Now fourth theory is dislocation movement theory. In this case, the dislocation moves during fatigue, and consequently a localized deformation occurs in the slip bands, and this deformation is called extrusions. In this case, some metal is expelled out of surface, and the extrusions are always accompanied by intrusions. This type of behavior where it is showing some formation of a crack. So these extrusion and intrusions, these appear as early as 1/10 of the whole life of specimen and have a height of 10 to the power minus 5 to 10 to the power minus 6 mm, are responsible for the initiation of crack. Next is crack growth rates. In aircrafts, but also in other structures as well, it is vital that engineers be able to predict the rate of crack growth during load cycling so that the part in question be replaced or repaired before the crack reaches a critical length. A great deal of experimental evidence supports that the view that the crack growth rate can be correlated with the cyclic variation in the stress intensity factor. So in this case, dA upon dN, A is your crack length, N is number of cycles. So this left hand term is crack growth rate per cycle, and delta K is your K max minus K minimum, which is stress intensity factor, and A and M are constants. These parameters depend on material, environment, frequency and temperature, and this is sometimes also known as Paris law. Now initial steep region, this region, it has low delta K values which shows no crack growth rate, and in case of linear part, this is the stable crack growth. In this part only your power law behavior is shown, which is known as Paris law, and after this in third region, final steep region, you see unstable crack growth. Now the rate of crack growth as a function of number of cycles is plotted against a stress intensity factor range. This plot shows sigmoidal type of behavior divided into three regions. Region first is crack initiation stage, second is crack growth stage, third is unstable fracture. This region 2 where power law is followed is used to predict fatigue life of various assemblies. Now for the 9th chapter, firstly we studied why pure metals are alloyed. So in this case, yield and tensile strength can be increased if we are alloying some materials. Then it can also increase hardness. Melting point of solvent can be increased. Your strength of solvent at high temperature can be dramatically increased, and corrosion resistance can also be improved, and it can also improve the manufacturability. For example, if you are reducing the melting temperature, if you are making some eutectic mixture, then for example in cast iron, it is improving its manufacturability. And this is your materials engineering workflow. In this case, your processing of material decides the structure of material, and microstructure of material, it decides what will be the properties, and these properties decide what will be the performance, and based on that we decide what will be the application of material. These all four things, they are interrelated to each other. Now basic definitions, a lot of questions were asked in assignment, a lot of questions were asked based on these definitions. So first is system. It is the series of possible alloys consisting of same components but without regard to alloy composition. For example, iron carbon system. So if you are getting different compositions, that will be part of a system. Second is component. Component is a pure metal or compound of which an alloy is composed. Phase is homogeneous portion of a system that has uniform physical and chemical characteristics. Then homogeneous system, it is a single phase. Mixture or heterogeneous system will be having multiple phases. Then solvent, it is a component in large proportion or the host. Solute is the component that gets dissolved or the gassed atoms. Next up is Gibbs phase rule. In this case, it has a criteria for the number of phases that can coexist within a system at equilibrium. So, and the formula for this is P plus F equal to C plus N. P will be your number of phases present, F is degree of freedom, C is number of components comprising the system, N is the number of non-compositional variables, which are temperature and pressure. In case this is the phase diagram for the water H2O. Here with varying temperature and pressure we can get different phases. So it will be either in liquid phase, solid phase or vapor phase. Next is Hume-Rothery's rules. In this case, for a binary system to be a isomorphous system, these rules are required. First, the greater the difference in size between solute and solvent atoms, the lower will be the solubility limit. So for example, for 100% solubility limit, it's possible if the size difference is less than 8%, and if there is no solubility for size difference greater than 15%. Second, greater the difference in electronegativity, lower will be the solubility, because then your material will more likely to form intermetallic compounds. Third is greater the difference in valence number, lower will be the solubility. And 100% solubility is possible only if solvent and solute have some same equilibrium crystal structure. For example, in copper and nickel, they both have FCC type of structure. Now next is type of phase diagrams. Type 1 is amorphous type of system. In this case, it shows 100% solid solubility, and these are substitutional type of systems. Now in this case, two metals will have same type of crystal structure and atomic radii will differ by less than 8%. Copper nickel system is best example for this system. In this case, region below solidus line is solid phase. In between you have liquid plus the alpha, the solid solution. Above this liquidus line you have liquid solution. And the chemical composition and relative amounts of each phase of mixture is not known directly. So here by using Liver rule you can plot a tie line at a constant temperature. Then using that you can find out what is the percentage of phases. Now how you get phase diagrams? So for various compositions you plot these cooling curves. Now based on these cooling curves, they are superimposed in these phase diagrams. For example, T1, T2. Now on this T1 it will start solidifying, and at T2 it will complete solidification. So this is how you can superimpose and form your phase diagrams. Now each cooling curve above is separate experiment starting from 0 time, and pure metals, they show a horizontal line as the phase transformation solidification happens at constant temperature. And for the composition 80A and 20B, first break is at T1 and second break is at T2, which means that solidification starts at T1 and ends at T2. Second type 2 of phase diagram, it is eutectic with having complete solid solubility. Now this phase diagram consists of four areas. Area above liquidus, above this is the single phase liquid solution, and below this you are having solid A plus liquid. Here you have liquid plus solid B. Here you have solid A plus solid B. So in this case you'll be having this red line corresponds to liquidus and green line corresponds to solidus line, and E point is eutectic point. In this case eutectic composition, here E is 40A and 60B. It is cooled from T0. Now at this point it is liquid, then at this point it will completely solidify into solid A plus solid B. So liquid converting into solid A plus solid B, this will be your eutectic reaction. Eutectic solidification is incongruent because of the difference in composition between liquid and individual solid phase. Type 3 is eutectic reaction with partial solid solubility. Now two metals completely soluble in liquid state and partly soluble in solid state. Now most metals are partly soluble in solid state, hence this phase diagram is most common type. Here your liquidus line will be above this one, TA, E and TB, and your liquidus line will be TA, F, E, G and TB. Examples of these are copper Ag, lead tin and tin bismuth. This is the lead tin system. This is how the solidification will be seen in these. So in first diagram we can see if the composition is before the solubility limit. So in this case you'll be here forming alpha particles, then only this complete solid solution will be forming. In this case you are taking it in solvus line region, then below solvus region you will be seeing there will be precipitates forming of beta. Here eutectic reaction won't be forming, you will be getting beta in form of precipitates. While if you are taking a composition which crosses a eutectic line, then there will be formation of beta in form of eutectic line, and there will be some pro-eutectic phases forming. Next is eutectoid reaction. It is a common reaction in solid state. Here solid 1 will be on cooling will be giving solid 2 plus solid 3. And first is a solid phase transforms into two new solid phases. The resultant eutectoid mixture is extremely fine, just like eutectic mixture, and it is difficult to find if the mixture is from eutectic reaction or eutectoid reaction under microscope. And the point M here, it indicates the allotropic change for the pure metal. So for example, in case of your iron carbon system, at M your gamma transfers into alpha, so it will be allotropic type of change. N is eutectoid point. At N your gamma is converting into alpha plus beta. Next is peritectoid type of reaction. It is also a common reaction in solid state. It is inverse of your eutectoid reaction. Here the new phase is usually an intermediate alloy or sometimes a solid solution. HP is the peritectoid temperature line, and here solid 1 plus solid 2 will be converting into solid 3 on cooling. So here in this case here your 1 solid, your 2 solid, alpha plus beta is converting into gamma. Some other reactions consist of monotactic reaction where your liquid 1 will be converting into different liquid composition plus solid. Other is peritactic. In this case liquid plus solid 1 will be converting into different solid 2. Next is iron carbide equilibrium diagram. So first is why we choose iron carbon system. In this case steel is by far the most used metal by the industrialized society, probably the only alloy system that is studied in the greatest detail compared to others, and it provides a detailed understanding of the solid state reactions in general. And this is the uh, cooling curve of pure iron. So if you cool pure iron, firstly it will solidify at 1538 degrees Celsius. Then delta iron will convert into gamma iron, which is non-magnetic phase. Then it will transfer into alpha iron at 910. Then your Curie temperature is 765. Below this it will be magnetic. Now as we start adding carbon, so we see these lines, and so for Fe3C diagram, for Fe3C diagram, it is not a true equilibrium diagram, and equilibrium implies that the phases do not change with time. However, in case of your cementite, it decomposes to iron and carbon, and this decomposition takes an extremely long time. For instance, at 1300 degree Fahrenheit, it takes several years to form iron and graphite. Hence, for practical purposes, it can be considered an equilibrium diagram. And this is the iron carbide equilibrium diagram. It is only a portion of iron carbon equilibrium diagram because it is going only up to 6.7 weight% of carbon. In this case, this is your peritectic point, and here it is eutectoid point at 0.76 weight% of carbon, and 4.3 weight% carbon it shows eutectic point. Your maximum solid solubility will be 2.14 weight% for gamma austenite, and austenite will be having highest solid solubility for carbon. In case of eutectoid region, gamma, so here 0.8 weight% carbon, it transforms into ferrite plus cementite. Ferrite will be having 0.025 weight% carbon. Cementite will be having 6.7 weight% carbon. And the relative layer thickness of ferrite and cementite in pearlite is 8 to 1. So 8 will be for ferrite, 1 will be for cementite. Mechanically, pearlite has properties between soft ductile ferrite and hard brittle cementite. It is a composite like structure, and the phase transformation requires a redistribution of carbon by diffusion. So here firstly a cementite layer will be forming, then in adjacent regions you find that the carbon will be depleted, so ferrite will be forming, then in their adjacent regions again cementite layers form, and hence it keeps on going, and the growth of perlite occurs. Homogeneous nucleation, solidification of a pure metal. So here we assume the nuclei to be spherical in nature, spherical in shape and having radius r. So there are two contributions to free energy change. First is free energy difference between solid and liquid phase, which is volume free energy delta GV. Here we note that delta GV is always negative below freezing temperature, and the contribution from solid liquid phase boundary during the transformation or surface energy gamma. So total free energy change will be volume free energy plus surface energy, and so delta G becomes 4 by 3 pi r cube times delta GV, because it is per unit volume, so we have to multiply volume and volume of the nuclei. Here you have to multiply with surface area, so this is surface energy per unit area. Now this is your surface energy, which is positive. It restricts the formation of nuclei, and the volume energy is the driving energy. So this increases faster as it has cube in it. So this curve firstly goes above, then it comes down in negative side. So at the highest of the this energy, total energy, you will be finding it's the activation energy, activation free energy delta G star, and corresponding to that you have R star, which is the critical radius. Homogeneous versus heterogeneous nucleation. So in case of heterogeneous nucleation, it refers to the nucleation starting on pre-existing surfaces and interfaces. And nucleation on flat surface, it has three interface surface energies: so solid liquid, solid interface, and interface to liquid. These three energies. So by balancing these, we get gamma IL equals to gamma SI plus gamma SL cos theta. And the activation free energy delta G star for heterogeneous nucleation is lesser than delta G star homogeneous, while R star remains the same. Hence the heterogeneous nucleation occurs readily and at an undercooling of few degrees Celsius rather than few hundred degrees Celsius in case of homogeneous nucleation. So as you can see, for heterogeneous nucleation we require less undercooling. The size of product phase particles depend on transformation temperature, and the transformation taking place close to melting temperature has low nucleation rate and high diffusion rate. So from these curves we can see this is the growth rate and this is the nucleation rate. Nucleation rate increases at lower temperatures and growth rate is higher near melting temperature, and overall transformation rate is given by this blue curve. So if we are near melting temperature in undercooling, then we see that the growth rate will be higher and nucleation rate will be lower. So less number of nuclei will be forming and the growth will be high. So you will be finding a coarse grained microstructure, while if you are providing high undercooling, then you will be getting fine particle and fine structure. And if material is cooled rapidly in the transformation temperature range, this situation corresponds to very low transformation rates, and thus probably producing non-equilibrium phases. Next is isothermal transformation diagram. So in this case, temperature plays an important role in rate of the austenite to perlite transformation, and the temperature dependence is shown in the figure in the form of an S curve plotted with percentage transformation. So this is the percentage transformation and it is starting at this time. This is the incubation time. After this it will start and it will finish at this time. This time you will be getting 100% perlite. So the S curve is plotted with percentage transformation with respect to time in log scale. For each curve, data are collected after rapidly cooling a specimen composed of 100% austenite to temperature indicated and holding at that temperature throughout the reaction. Now these curves will be different at different temperatures, and then these curves, they can be extrapolated at these at this your isothermal transformation diagram. So these graphs are plotted by these uh, these transformation curves. Now more convenient way of showing the temperature dependence of this transformation is shown in this figure. So in this case, your vertical axis is temperature and time is on x-axis. These curves are generated from a series of experiments at different subcritical temperatures and then transferring the data as shown for one temperature in the figure. Now, similar to this, there will be a lot of more curves which are extrapolated in this curve and are found in this terms. Here this green line is where transformation is ending. This blue line, dashed line, is for 50% completion. Red is for beginning of the transformation. Before this, it is the incubation period. Now the sample cooling of an eutectoid steel. A cooling curve ABCD is superimposed on the isothermal diagram. So very rapid cooling of an austenite to a temperature is indicated by near vertical line. This AB line, this is rapid cooling. Then it is this BCD is your isothermal treatment. Here you are holding at a constant temperature. Between C and D, your transformation is taking place. Your austenite is transforming into perlite. The transformation starts at 3.5 seconds and finishes at 15 seconds. And the thickness of ferrite and cementite layers in perlite, it depends on the transformation temperature. At high temperatures, carbon can diffuse long distance, hence it forms thick layers leading to coarse perlite. And at low temperatures, diffusion is less and hence fine perlite results. Triple T diagram for the eutectoid steel. Now austenite transforms to another product called bainite in feathery structure at low temperature, while at high temperature you see that austenite converts into perlite. Austenite transformation to another phase called martensite, needle-like structure at much lower temperatures, and austenite to martensite transformation is diffusionless, unlike austenite to austenite to perlite or austenite to bainite transformations. So if you cool it very fast and enter the MS and MF, then you see your steel will be transforming into martensite. This martensite is a non-equilibrium phase and hence it does not appear in the iron carbon iron carbide equilibrium diagram. This is the formation of pearlite and bainite. So in this case, pearlite will be forming by first formation of Fe3C, then formation of uh, ferrite in adjacent part, and in case of bainite there are two types, upper and lower bainite. In case of upper bainite, you see firstly ferrite nucleus will form in both cases, then the in upper bainite there will be formation of Fe3C, and in case of lower bainite there will be epsilon carbide forming, which will be inside this ferrite in this ferrite nucleus. And these are the micrographs of upper bainite and lower bainite. This is the martensite. So martensite has BCT type of structure, and in this case it forms when austenized iron carbon alloy is rapidly cooled. And martensite is a non-equilibrium single phase structure. It is formed by diffusion less transformation. In this case FCC austenite changes to BCT martensite. Now previously we saw isothermal type of transformation. Here it is continuous cooling. So in this case you will be cooling your steel continuously rather than isothermally. In this case your plots are a little bit to the right side and shifted to the lower side, because here you are providing less undercooling. So isothermal diagrams can't be used when cooling is done continuously, and the diagram must be modified for transformations that occur as the temperature is constantly changing. And for continuous cooling, the time required for a reaction to begin and end is delayed. This diagram is called continuous cooling transformation diagram. Here MS and MF line occurs at the same temperature for IT and CCT diagrams. Now these are the two continuous cooling curves. So for the slow cooling curve will be forming coarse pearlite, while for the moderately rapid cooling we find fine pearlite. If this there will be one more curve which will be missing this nose, then it will be forming martensite. So in continuous cooling bainite is not formed, as the transformation to pearlite would have finished before it reaches the bainite temperature. Hence the diagram doesn't have lower nose region and the transformation terminates along AB curve. Now these are the microstructure and cooling rates. So along the nose temperature, this is called critical cooling rate. Below, if your cooling rate is higher than this, then there will be martensite forming, and above this martensite plus pearlite will be forming, and if cooling rates are slower, then pearlite will be forming. And some alloy steels you can also get bainite formation. So bainite region will also be there. So there will be these mixture of phases that can form.